In this video, we're going to look at a wire which is coiled around, making many loops as it turns around. And this such a wire is called a solenoid. And we're assuming this is going to be in a vacuum for this case. And we'll look at what's the magnetic field inside all these loops. And the first question is, what's the direction of the magnetic field inside the solenoid? And the second question is, does the magnitude of the magnetic field inside the solenoid depend on which one of these factors? So first of all, does it depend on the number of turns? Do you expect the magnetic field to be greater or less, or proportional or inversely proportional to the number of turns? Does it depend at all on the magnitude of the current? Does it depend at all on the length of the coils? Does it depend at all on the radius of this coil? Does it depend at all on the permeability of free space? If so, answer proportional, inversely proportional, yes or no, and then try to come up with this equation here to just see, does it make sense which one of these terms are important, and it should be proportional or inversely proportional to them. So pause the video now, and once you think about each one of these factors and say, does it depend on these at all? If so, would the magnetic field get larger or would it get smaller? Would it be inversely or directly proportional to which one of these terms? So pause the video and write your answers. For directionality of magnetic fields, we need to think about the right-hand rule. So the right-hand rule says, I put my thumb as my input, put it whatever direction the current's going, and then I wrap my right hand in the direction. For example, if this current's going down here, that's the direction, so the magnetic field is encircling this one. If a wire here is going up here and some section of it straight, thumb in the direction, so the magnetic field is circling it there. If some section of the wire is in this direction, my thumb in the direction of current and wrap around the magnetic field direction. So this is telling me, so I can kind of look at different sections and see which way the magnetic field is going. So you can kind of do, so say the wire is coming around here, so it's coming in the front first. Let's say it wraps around the front and then it's kind of going back into the board. So this part's out of the board more, and this is in more back behind the plane of the board. So I have in front this current coming down, and they put my thumb in the direction of it, and I wrap around. And you can kind of see that this loop's coming around, and so you see my fingers in the middle are inside that loop, saying the magnetic field is going to the right. And so then if I look in the back, so for example, so assume this is way behind, over here behind the sheet. It's going up. Now if I wrap around and I'm saying inside this loop, the magnetic field is again going to the right. And if then on the loop part, and the part going around and so there's a plane like here. This is looping around, and the current's going there. So if I loop around there, again I see that this field's going through there. Another way that might be easier to see is if I just said, let's take a view from this end, and if I saw that, I would just see this circle right here, okay? And then this part would be the part which is out in the front here of that loop, okay? Because I'm looking here and I see this part is on that part, and again so that goes with this current's there. So now if I put my thumb in the direction of the current and wrap around, you can see that outside I'm going into the board, and then inside I'm coming out. So that's approaching my view. And then we'll pick this one. So this is back behind the board running around. The current is going now up, or coming back up through that loop. Put my thumb in there, and inside these coils is coming out, and outside is coming in. And I can do the same thing on this top as it's coming around. Thumb in the direction of the current, inside the solenoid coils is coming towards my view, and outside it's away. So you can see every place, every little segment around this thing. So I have a segment of current here. There's everything saying magnetic field is going to the right inside the coil. Now, so that means I have all these lines of magnetic field, this directionality, okay, going this way, and it's exiting here, and somewhere in the round here is looping around and is coming back through here. So that makes this the North Pole and this being the South Pole. So inside the fields lines are all going this direction. Okay, then it exits the solenoid and it has to start, it's like a magnet, it's going to start looping around and come back around into the cell side. So that's the answer for the direction of the magnetic field. It's running this direction. Now if I turn the current the other way, then it would run the opposite direction. So now let's think about magnitude. Well, first of all, we'll think about magnitude of the magnetic field around a straight section of wire. So that depends on the permeability of free space divided by 2 pi times the magnitude of the current going through it, and then the distance. So the farther away I get from that wire, the less strong the magnetic field is. So that we'll keep that in mind. But now we'll just think about this case. So, what do you think? So the number of turns. So think about it. Each little turn can be thought of like a disc going around, and that current going around there that makes that magnetic field. So if I have lots of discs kind of stacked upon each other, I'm essentially having more. So each one is kind of adding up and contributing to this magnetic flux. So you think, yeah, the more turns I can do, and the reason why I'm putting the solenoid together is to get a strong magnetic field. I'm looping lots of loops to get that, because they're all kind of adding on to each other to make this stronger. So it's proportional to the number of turns. So yes, it is. Yeah, it does depend on the number of turns, and it's proportional. The more the number of turns, the greater the magnetic field inside. So it's yes, it matters, and it's proportional. So therefore, we would expect that we'd have n to make it proportional. The current. So yes, you'd think that the higher the current level, well, the more magnitude of magnetic field I'm generating. So you'd think, yes, that would matter, and it would be proportional. Higher current, greater magnetic field. So we think, current, the magnitude of the current, we think matters. Does the magnetic field depend on the length of the coil? Just think about it. So let's say I had one turn here, and then I took a long time to get another turn, and then another long time to get another turn. Would that be a stronger magnetic field, or if I try to loop them all close together? Well, yeah, I'd be stronger if I can try to loop them all together and tie them packed tightly so I can get more turns in a short length. So yes, it depends on the length of the coil, and it's inversely proportional. So I want to have lots of turns in a short length. Does the magnitude of the magnetic field depend on the radius? So whether it's looking from the end is if this diameter is a small diameter or a big diameter, does this magnetic field magnitude depend on that? Well, this depends on how far away I am. Well, it turns out that it doesn't. It doesn't matter. It had the same magnetic field magnitude whether this was a huge wrapped around something huge or wrapped around something very small. But one thing to note is that, unlike this, which is kind of shown, I kind of did these points, this magnetic field, which is running to the right on this one, it's uniform, basically approximately uniform throughout the whole thing. So it's these lines, magnetic field lines, are running everywhere inside this encircled coil, but it doesn't depend at all on the diameter of this. So there's no diameter term in this equation, unlike this equation. Does it depend on the permeability of free space? Well, that equation does, and permeability kind of relates the equation. So permeability, if you recall, previous space is 4 pi times 10 to the minus 7 Tesla meters per amp. Trying to stay consistent colors here. So permeability free space does show up there. Okay, proportional just like there. Is there a 2 pi needed here? Just like this, you kind of think about it. The circumference of this circle here is 2 pi. So, and if I go farther out, I kind of get this. It's always still 2 pi. So that's kind of taken care of here. And so this is the complete equation for the magnitude of the electric field inside a solenoid when it's operating in a vacuum. If there is a material in it other than just a vacuum, if you have a piece of metal or something, then you would just replace this permeability of free space with the permeability of the metal. So you can get a stronger magnetic field if you put something in there besides just a vacuum. If it's just air, the permeability of air and the permeability of a vacuum are very close, and it's typically just still use that number for air. But you put something else there, you can generate greater magnetic force. But this is in general the equation for the magnetic field through a solenoid, a loop of coils, dependent on permeability of free space, the number of turns per length, and the magnitude of the current. And you can see, always a good check for units, you can see that that using permeability of free space, a Tesla, I get there, and then meters for here, I got meters on the bottom, I got amps on the top and amps on the bottom. So and N is just number of turns, it's a number, it doesn't have units. So this answer does turn out to be in Teslas for SI units.